Hello there.
Hi,
Hello, how are you doing?
I'm doing good. How are you?
I'm great. Um, I really appreciate you taking your time to come meet with us today. We
Yeah,
we found
yeah,
your research really interesting. We love some of the stuff that you're doing with Climax, and we thought it was just your general line of work with AI and climate change. We thought it was really interesting. We just wanted to learn more, so
yeah,
we had some
yeah,
questions.
yep.
Do you mind if I record this and do share it?
Yeah, that is fine. Yeah.
Okay. All right, great. So. Yeah, so what can I address you by here?
You can just call me Tung, Tung. That's my first name.
Okay.
Yeah.
What year in your PhD are you at right now?
So I just finished my third year. So 2 more years to go.
Almost there then. Soon
Yeah,
to be doctor.
yeah.
Nice.
Hope so. Yeah.
All right. Yeah, awesome. Yeah, so yeah, maybe we can get started here. So
Yep.
just wondering, Tong, maybe you could just maybe tell me a little bit about yourself and your journey in artificial intelligence, climate change, computer science.
Yeah. So I started as a undergraduate student in Vietnam, and I was a student in computer science. Um, and then I think I started doing AI in my second or third year of undergrad. And at that time, I was just like joining a research lab in my school and just like working with the professors there. And then started gaining some experiences. And then I applied. So there was like a AI residency program in Vietnam that was opened by a private company,
Sure.
and that program was supposed to like train young people, young and talented people to become experts in AI and then maybe to do a PhD in the US. So I joined that program and I spent 2 years in that program. I gained more research experience. I got some papers and then I applied for a PhD in the US, and then I came here in 2021 at UCLA. Um, and yeah, so I'm still working on my PhD right now. So I think before my PhD, I actually worked on something slightly different. So everything has always been AI related. But before my PhD, I had a slightly different topic that I worked on. However, when I started my PhD, I wanted to do something more applied, something that um, is not only interesting or exciting to machine learning or AI people, but also to general public.
Sure.
So that's why I started doing climate change related research, and started building or and developing AI models that can, predict the weather, model the climate, and so on. And yeah, so I think that's basically sums up my journey until now.
Sure. Right. Would you say there's maybe a moment or, some specific instance or some moment particularly that really was a key factor in deciding your trajectory and going with computer science and AI? Or would you say it's more of a gradual progress? I think you mentioned that you started learning about your AI type thing in undergrad.
Mm.
Um, and you really influenced by the residency program. Would you say there's maybe a moment that you could point to, or just general process?
Yeah, I think everything was just a gradual process to me. Um, so I think I didn't really have a strong reason to like go into computer science after my high school. I think the only reason at that time was that I knew I wanted to do something like technical engineering kind of major. So I applied to a school in my country, and that school was very well known for like engineering, computer science, and mathematical majors. And out of all those majors, I don't know, computer science just seems the most exciting to me. I didn't even have any experience, any background in computer science before my undergrad.
Hmm.
But I think it's just seem more cool, I think,
Sure.
more interesting in some ways. Because like as a high school student, I didn't really know too much about different majors and how they differ from each other.
Right.
And I just chose my major based on just my emotion, my feeling at the time. And then,
Sure.
but then after like 1 year and 2 years studying computer science, I really like felt really interested in what I was studying at that time. Because like learning how the computer can actually make a lot of human tasks much easier and much more convenient for us. Um, and AI is kind of the same way, right? Because like what AI right now can even do more complex and more complex tasks and are becoming more and more useful. So I think that was always the reason why I wanted to do computer science and AI. Um, so everything was just like a gradual trajectory. There was not really a key moment at all. So I think the most important moment that leads me to the US to do my PhD was joining the residency program actually, because so doing a PhD in the US is not easy at all for people that are outside of the US.
Right.
So if they want to apply, they do have to have a lot of experiences, like research experience, even before they do their PhD. So in my country, in Vietnam, there was not a lot of institutions or a lot of companies that spend their money on doing research.
Sure.
And that was one of the very few that I could find in Vietnam. And I think I am grateful that I decided to join that program at that time. I think that was one of the most important moments in my journey so far.
Right. So you think that, joining the AI residency program really, it helped shaped the way that you were going to move forward in the future.
Yes. Yeah.
Do you know if you could, discuss what kind of topics that you worked on in the AI residency, or, because you mentioned that you're interested in climate change now, right? I mean,
Yeah.
I know you did touch on the fact that you were interested in something different in relation to AI prior to coming to the US, so maybe there's
Yeah.
something there that you'd like to discuss.
Yeah. So when I was at the residency program, I used to work on reinforcement learning. So
Okay.
reinforcement learning is a special kind of learning where you can teach a AI model by giving it rewards when it does something good and penalizes it when it does something poorly. Um, so I was working on that, and the specific topic that I was working on was I wanted all of these like AI models can, um, make decisions by only looking at the images that they can see using
Sure.
cameras.
Sure.
So for example, in factories, when people deploy a robot that can do some simple tasks,
Mhm.
um, they need to provide the robot, let's say, the exact position of the arm of the robot, like
Right.
X and Y values of the position of the arm of the robot, so that it can make decisions accordingly.
Right.
However, in more complicated cases, like more real world settings, for example, like self-driving car, when the
Right.
car drives on the road, you cannot always exactly tell where it is on the map or something like that. And everything you have is just a picture, an image taken from a camera. Um, and by only looking at that image and analyzing that image, it has to figure out where it is, where it is at, and what to do next. So that
Right.
was my general topic when I was in that program.
Okay, for sure.
Um, yeah, even though it was significantly different from what I'm doing now, I think still taught me a lot of like fundamental skills and knowledge in AI because everything is just um, I think they all have the same foundation in mathematics, statistics, and programming, and so on. So yeah,
Right. Okay, yeah, for sure. So I think
yeah,
maybe we'll pivot towards some of your more recent research now. Um,
hmm
so one of the research that we found interesting was Climate X, Climax, and then I know I'm not exactly sure if this is primarily like an extension of the project, but your more recent research on LICO, the large language model for mo
Mm.
molecules, if you could maybe like if there's one of those two, the climax or LICO that you particularly think is extra interesting or we might find interesting, if there's one that of those that you'd like to maybe give us a simple overview on, that would be really great.
Yeah, I think Climate Act is one of my favorite papers and one of my favorite projects. So I think I'm gonna talk about that. So Climate X was a collaboration between UCLA and Microsoft when I was an intern at Microsoft Research in Seattle. Um, so so normally what people do for weather forecasting is that people have to solve a bunch of equations. So let's say you have 1,000 of equations that relate temperature, specific humidity, precipitation, and the wind, for example. And then to make forecasts into the future, let's say you want to know the temperature tomorrow or 2 days ahead, then you
Right,
have to solve those equations and solve those equations across the entire Earth. And solving that equations, you have to use supercomputers. So
right,
all of the supercomputer clusters that are well known, like the one in the US, the one in China, and so on, they are their main purpose is to solve these equations for weather forecasting and for climate modeling.
sure.
However, that is very that is very computational expensive, as you
Right,
know, running these supercomputers is costing a lot of money
right,
and
right,
time
right,
as well. So what AI can do is AI can take data from the past. Let's say you have collected temperature data from, let's say, 1970 to 2020, for example.
sure.
Then you can train an AI model on that particular data set to perform weather forecasting. Sorry, to learn to forecast the weather from that data set. And then after learning, the AI can make very fast prediction by only using a small computer instead of running the supercomputers.
Right,
So that is the promise of AI for weather forecasting and for climate modeling. However, there is one problem. So most AI papers before my paper, all they do is that they take a certain data set and they train a specific model for that data set and to perform a specific task. So let's say weather forecasting. So one AI model can only perform one particular task, weather forecasting, for example. However, in AI, in other fields of AI, let's say computer vision or natural language processing, people started moving towards a more large
general,
scale and more general like
right,
regime where people train a single model on a lot of data that they can find, and then after training, that model can adapt to different tasks. So one of the prominent examples you can see is ChatGPT or GPT from OpenAI. So that is on we call it foundation model. So foundation
right,
model is like a big model that can do many things.
right,
And so we wanted to like we took inspiration from those other fields, and we wanted to do something for the climate science. So Climax was, I think, one of the first foundation models of weather and climate. And Climax could not only perform weather forecasting, but also climate downscaling, regional forecasting, climate projection, and so on.
right,
So yeah, that was the first paper that we showed we can do such a thing even in climate science. Um,
right.
yeah,
So one of the first instances of like general artificial general intelligence, because when we think of like that kind of thing, computer vision, as you mentioned, there is some examples of that dating previously, but I think your work on Climate X is really that first step in terms of forecasting, weather forecasting, just weather, everything about weather and climate.
yeah, it was more like a general purpose model. I think I'm gonna say that um, because it can be used for multiple purposes, basically.
Right.
Yeah.
Sure. So From that project there, what could you say are some key challenges that you really faced and overcame throughout the course of that?
Yeah, so I think in every AI project, going from the big idea into the detail is actually the most challenging process.
Sure.
So the main idea, as I said, is just to train a large model on a lot of data, and then that model will somehow achieve like general intelligence in terms of understanding the climate, and then
Right.
after training, it can perform a lot of different tasks. So that is the general idea. But how we do it in practice? For example, what data we train the model on? And the second question is how, like, what kind of model we are training? So the first question is not too difficult to answer because in climate science, there are many data sets because there are many institutions in the US, in the world that
Right.
are collecting weather data and climate data, and they have a lot of data that is public. So the number one question is not too difficult to answer. However, the second question is the key technical challenge in this project because one special thing about climate data is that each climate data set can be slightly different from the other.
Right.
So for example, one data set that I have can have temperature in it. The second data set may not have temperature, but may have precipitation or specific humidity, for example. And the third data set may not have precipitation or temperature at all, but may have the wind, for example.
Right.
So all of these variations um, are not typical scenarios in machine learning. Because in machine learning, deep learning, or AI, we always expect the input to be kind of like the same shape and the same
Sure.
dimension, uh, and not vary over time.
Right.
So that was the main technical challenge. So we had to like develop a new kind of like encoding system to deal with that variations across different data sets. And then after that, everything was well aligned, and we could train a model on that data.
Sure.
Yeah.
Um, would you say that that's a very complex process, or would you say that that's maybe, is that something you'd like to discuss maybe further about how that how you were able to develop the new encoding system? Because I think that's a very interesting point that, when I as a high schooler like experiment with AI models, they're typically, in PyTorch, right? For instance,
Mm.
we'll always like have, you know, the input needs to match what it was trained on, right? Or the input needs to stay consistent for the trained model. And the idea that some data has this and some data doesn't seems to me like a very almost a stopping point there. So I was interested in how could you speak to how you overcame that?
Yeah. Are you familiar with like CNN, convolutional neural network?
Right, right, yeah, yes,
Yeah. So the standard CNN, or I think the standard vision model, the way it works is that so like climate data is very similar to image data.
sure,
So you have so in image you have like RGB channels for red, green and blue. In climate, instead of having RGB channels, we have temperature as one channel, specific humidity as one channel,
right,
uh,
right,
and precipitation as one channel, and so on. So like you have a stack of physical channels or physical variables. And the main question now is how do we deal with the varying lengths or the varying number of channels in the data points. So the standard vision model would stack all these channels together, right? And encode all these channels at once together.
right.
For example, the CNN. Um, However, what we did was instead of stacking everything together as a single input, we basically split them into, let's say, there are five input variables coming in. Then we split them into five different images, basically.
Oh, sure.
Yeah, and then we process each image separately using a certain neural network.
Right.
And then at the end, we have a aggregation module that can aggregate these five channels into one uh,
Okay,
single
so you
end. Yeah,
right, so you process each of those multiple variables individually and then aggregate them at the end.
yeah, yes. So instead of aggregating at the beginning, like stacking them together and then processing them, we're splitting them at the beginning, processing them individually, and then aggregating them at the end.
Sure.
Um, So by doing that, you don't care what like how many variables are coming into your model because you are always processing them individually and you only have to aggregate them at the end. And the aggregation can handle any number of variables.
Right.
So that was the main, I think, technical like innovation of that of that
Yeah, for
project.
sure. I think that's definitely a very fascinating technical, like you said, technical innovation there because that really makes it, that simplifies the process for a lot of different data sets where there's that discrepancy in the types of data that's being inputted. One question I
Yeah.
do have coming off of that is, have you seen that kind of technique used in new research now that your model has been released? Is there some general adaptation of that sort of technique, considering that that's a big step forward, you know?
Yeah, so I think there was a recent paper by Microsoft. I think it was released a few months or a few weeks ago, and they are aiming to do the same thing as we did. So they're aiming to train a large neural network model that can do many things, and their main problem is very similar to what we had to deal with. Their data sets are very different from each other.
Right,
And again, they had to devise a new encoding method. And I think they took some inspiration from the Climate X paper, even though their encoding system is a bit different. Um, but it is the same idea that the main problem is in the encoding process. If
right,
you can handle the encoding to work with multiple variables, then everything else after that, after the encoding, will just be a normal neural network. It can be like CNN or transformers or anything, but
right,
the encoding is the main like bottleneck in those cases.
right.
So I think yeah, people started realizing the importance of having a flexible encoding system to deal with those scenarios. But
Right,
they
for
may not
sure.
be exactly, yeah, they may not be exactly the same as we did, like in terms of the exact implementation, exact technical detail, but they share the same spirit
Same
of,
idea.
yeah,
Right. No, I think that that's definitely an idea that maybe isn't, talked about a lot, that, you know, we definitely have an abundance of data as of right now. I'd say, like, especially for data heavy fields, like you say, like climate data, like, in the United States, you have NASA collecting a lot of climate data
mhm,
and probably lots of other organizations that are collecting data. But you're right. I think, when there's so much data available, you don't want to be limited by the fact that, oh, this data doesn't have temperature, so we need to throw it out, right? Or we can't
yeah,
use this data. So I think that that's definitely an important finding from your research there,
yeah, yeah.
right? So yeah, so just another extension off that. I know you touched on this before, but maybe you could just elaborate on some of the importance, the potential real world applications of that research there, the Climate X.
Yeah. So I think the Climate X was more like a proof of concept paper. So in academia, I think 99% or even more than that are more like proof of concept, where we have an idea, we propose that idea, we do some experiments to show that that idea works. But to show that idea works, we often have to restrict ourselves to a setting where it may not be realistic in real world, because that is how just academia works, because everything has to be standardized so that we can have a fair comparison with other people and with other models and so on.
Right,
However, I do believe it is only a matter of like spending more time, more money on scaling up that model, that technique, uh, to a much larger data set, to a much larger model, and then like deploying that model on a server so that it can like, for example, perform weather forecasting operationally, like every day, and setting that forecast to your phone, for example. It is only a matter of like spending more time and more money on that. So I do believe many of the existing AI research on climate science is actually very close to real world application. And I know, for example, people in UK, so Google DeepMind in UK, they have a very close collaboration with the MedNet. So MedNet is like one of the biggest climate institutions in Europe and in the world,
Sure.
actually. And they have a very strong and close collaboration. And whenever Google DeepMind has something new and is promising, then the MedNet department can just take that model, deploy it on the server, and actually produce the forecast for everyone to see in real time. So yeah, it is only a matter of like uh, you're spending more time and effort to make your
Yeah.
work more close to like real world.
I think that's something that that's been really discussed a lot. I think academia always has, you know, they're always like we're always restricted by, lack of funding or we need some more resources.
Yeah.
And you don't get to that level until you can involve some corporations, which I know that you did work with Microsoft there. So I think, maybe like you said, very close to that next step and taking it to maybe public usage.
Yeah, but I also think that is still that has always been the main purpose of academia, like innovation, research, new
Sure.
ideas, and then whoever wants to take those ideas into a next level, even in within academia, if people want to do so, they can do so. But I mean, the main purpose of like academic research is to have like to bring in new ideas, bring new solutions. Those solutions don't have to be deployed in real world directly, but um they can be taken to the next level by anyone else outside of academia or inside of academia.
Sure.
Yeah.
Okay, for sure. Yeah. I mean, I think we could discuss Climate X for a long time. It's a very, very, very packed paper there. I think a lot of great research. So I think I do want to take a step out from the Climate X
Mm.
point of view and just ask you some more like just general questions about the intersection between AI and climate change. So maybe one question I do have here. How do you like think of, we talked about foundation models a little bit. How do you see the role of foundation models evolving in terms of like environmental and climate sciences? And like what potential benefits or even challenges do they present as we move forward?
Yeah, so I think foundation model has a very potential in climate science. And so the main, I think the main selling point of foundation model is that you only have to train a big model once and you can use that many times. So for example, like GPT, right? So GPT-3 was trained in 2020, and then nowadays still people are using it for many like natural language processing
Right.
tasks. And I'm seeing the same thing for climate science. Let's assume we can train a big model like GPT, but for climate science that can perform many tasks, then that is useful for many people in many institutions. So, for example, some people in a research lab, they don't have a lot of compute. They just they can just take this correlation model and do something with it on their data, on their problem, and they may come up with and that may be useful to their research or even to their deployment of a climate model. So I think foundation model that is the main selling point of foundation models. Um, and I do see a lot of use cases of that kind of model in climate science because, as I said earlier, many people, many research labs in the US are doing climate science and climate modeling, um, and they can benefit from such a model. And then I think the second reason is um, yeah, basically we have a lot of data that we still haven't explored. So GPT, I think, or OpenAI, I think they have already exhausted the internet text data. But for climate science, I don't think we are even close to that. I think we have a bunch of data that are still underexplored. So if
Right.
we
And
can
that's
actually, yeah,
sure.
and
That's
if we can make use of that data to train our model, then I think it will be very strong, a very strong model and very
right.
useful model.
And that's partially what your intent was with that that other your other large your more recent large language model, the Lyco model, exploring some more of the climate-based data with the molecules.
No, yeah. So the actually the LICO paper, it is actually on a slightly different topic.
Sure.
It is still like foundation model kind of research, but it is on like another domain.
Okay, okay.
Yeah,
Right.
different from the climate domain.
Right, but still exploring that idea of that, like there's so much data available, and we're just now getting to that point where we can harness and create foundation models to access all that.
Yeah. So that paper is, I think, all that paper is about now we have a foundation model like the Llama model by Meta. How do we make that model to work to our own problem? If
Sure.
even if it is not a language problem, can we still use that model in some ways? Um, so yeah, so I think there are two sides of foundation models, training and using it. So training, we already know is important, but using how to use the foundation model for our own problem, that is also a very important question to answer. Because
Sure.
yeah, in some cases it may not be obvious to answer that question.
Right. Okay, for sure. Yeah, that's a lot of the questions I had here. I think a lot of the stuff I had was related to that climate X research. I think, that's I I used to work at a lab in the Boston area, which was heavily focused on temporal
Mm.
regarding nowcasting, like
Oh yeah,
rainfall nowcasting. And I think even in my review of papers and review of other information, the Climate X paper was definitely one of those papers that we really looked into a lot.
yeah, yeah.
Right. I think it's a really key paper in the field right now. So I think that's great. Um, and yeah, so if you didn't have any other questions for us, I think that is primarily all our questions here. So yeah, I mean, really appreciate all your time here, Dr. Nguyen. And I think good luck with the rest of your PhD.
Oh yeah, thank you so much.
Thank you so
So
much.
feel free to email me to
Sure.
ask any other questions you may have. And yeah,
Sure.
thank you
Right.
again for inviting me.
Of course, of course. Yeah, we really enjoyed the work. Thank you so much.
Oh,
Have a great
yeah,
day.
yeah, you too. Bye bye.
Bye bye.